Assalamualaikum warahmatullahi wabarakatuh to Prof. Nadia IR Dr. Hisham bin Abdul Rahman. We are from 27 going to present our high voltage engineering assignment. So these are our group members. We have Nur Nazila, Nur Nazira Shazwani, Nurin Sofia, Nurin Husi and Nurul Hamzah. For problem statement, when constructing of a headline insulator, the problem statement is to ensure that the insulator can properly sustain and insulate high voltage power transmission lines from their supporting structures and ground. So this insulator must be able to endure the system electrical and mechanical loads such as lightning strikes, wind, and temperature fluctuations without failing or degrading over time. The objective is to develop an insulator that is dependable, long-lasting, and cost-effective, while also fulfilling safety and performance requirements. Next, for objectives, we have three objectives. First, to design a model of insulator for 275 kV by using high tempered glass material. Second, to simulate the performance of the proposed design by using FEMM software. And third, to analyze insulator performance using a high voltage experimental setup and method. Next, these are our scopes. First, to create a model of an insulator that can withstand a high voltage of 275 kV. Second, to evaluate the performance of the insulator design in terms of electrical field distribution, voltage gradient, and related parameters. And third, to evaluate the performance of an insulator under high electrical stress conditions using a high voltage experimental setup and method. Next, for technical summary of chosen concept design. So the insulator shown here is the chosen concept design that has a full rod string structure and also consists of the insulator is made up of a continuous string of rod-shaped components. A high-tempered glass dielectric substance is used in this concept design, and we use 15 disc sheds in our insulator design. So this is the parameter of our concept design. We use the system voltage is 275 kV. The type option is full rod string. Fitting cemented cap type. Type of shades is standard shade. Number of shades is 15. Material option is high tempered glass. This insulator height measurement is 146 mm and the diameter is 255 mm. The insulator length is 2044 mm. So the total length including and fitting is 2180 mm. So the creepage distance is 330 mm. Next, the technical summary of FEMM simulation software. The electromagnetic performance of the 275 kV insulator with a full rod string and high tempered glass dielectric material may be analyzed using the finite element method magnetic FEMM simulation software. The FMM simulation begins with the creation of a 2D or 3D model of the insulator geometry, which includes the whole rod, string structure, and high tempered glass dielectric material. The FMM software allows to analyze numerous performance characteristics of the insulator design based on the simulation results. After conducting the FEMM simulation and obtaining the results, we need to analyze the distribution of electric field strength over the insulator surface and find the regions with significant field concentrations. And next, we need to determine whether the electric field strength reach the specified insulation levels and if there are any possible areas of electrical stress. We also need to identify the stress concentration points such as sharp corners, interfaces between materials or places with non-uniform electric field distribution. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Nazila binti Muhammad Usni. I will continue for process flow finite inlet analysis simulation to the prototype. First, I will explain about the block diagram. We propose an insulator design, then design 2D design using AutoCAD software. Then we set the parameter of the insulation. We modeling the design into FEMM software, simulate and analyze the design insulator, and lastly we record the result. So next is the flow chart. We start on discuss on how the insulator design type and material. We design a 2D 275 kV and 15 disc insulator using AutoCAD software. Planning the coordinate of 2D drawing in FEMM software, we draw and connect the coordinates to form an insulator. Match is define material properties, condition and match the design. Analyze the voltage and electrical field. We simulate, troubleshoot and record the data. If there is error on mesh, we have to check the connection, the coordinate from the insulator, and then it's the end. So for technical summary methodology of FEA simulation, first, create a 2D geometry and mesh generation. It needs to be carefully designed and analyzed. The prototype needs to be built to bear mechanical and electrical strains. Then match the geometry to make it discretized into finite elements. Second, assigning appropriate material properties and boundaries condition. These properties may include mechanical and electrical properties. Also need to specify the boundary condition by applying loads or electrical component. The third is the FEA software solver are required for the insulator prototype analysis. For a structural problem solver, such as one that can handle static or dynamic analysis, is chosen as mechanical analysis. Solver that can resolve electrical field equation is chosen for electrical statistics. Next is we determine the mechanical and electrical response of the insulator prototype. This includes solving a system of equations that defines the behavior of elements and their interconnection. Result of the investigation includes voltage gradient, electrical field intensity, stress distribution, and more. Lastly, iterative process help improve the accuracy and reliability of the prototype design. We need to verify the accuracy of model. The simulation results are compared with experimental data or analytic answer. If any applicable such as changing the shape, mesh or parameter until the simulation outcome are consistent with the predicted behavior.
Assalamualaikum, my name is Nana Srazwani binti Muhammad Fauzi, DE200113. Today, I will present about the simulation result of our insulator. So, firstly, the simulation is conducted using FEMM finite element analysis software, which to comprehend the class insulator behavior for 1 unit disk and 50 unit disk, or we can call as a string class insulator. In this simulation, we will consider two conditions, which is in normal condition or dry condition, or second condition is in wet condition. And the model of each class string is represented in a 2D asymmetry domain, and the simulation is performed in steady state current flow. And this is using the material properties in the table below, which is the material used in the simulation is air, cement, glass, iron, and water. As we can see in this picture, it's a single unit glass disk, which is we declare the iron part here, we declare as a high voltage, which we insert the value of 275 kV, and the blue one area is we define as a ground. So we can see the EMF wave from the high value area to the ground. As you can see here, also we obtain two graphs, which is voltage versus length of insulator and electric field intensity versus length of insulator. Both graph is in dry condition, which is the insulator is in dry condition. In this, in the first graph, the voltage also decrease linearly corresponding to the length of the insulator. And the second graph is we can see the graph reveals that the initial portion has a bit higher field intensity compared to the rest of the insulator. And when at the ground connection, the electric field intensity is initially higher than the initial condition of the insulated value. Next, 15 unit glass string insulator. In this simulation, we simulate the insulator in second condition, which is in a wet condition. For the simulation, we add a mixture of water with the permittivity of 81 that we add on the glass surface of the insulator. You can see this is the result of the wet condition, which is the range of 5.319 V/m. And then next one is the electric field distribution for the wet condition result. So as we mentioned, the blue color represent the low electrical field intensity ranging from 0 volt per meter until 9.111 multiplied by 10 power of 5 volt per meter. Also, in this condition, we come out with two graphs, which is voltage versus the length of insulator and electric field intensity versus length of insulator. In this graph, it illustrates that the electric field intensity start at a higher level and gradually decrease as the length of the insulator increase. However, starting at this point, the electric field intensity suddenly spike until they reach the maximum value at a certain point, indicate the presence of the contaminant.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Husni binti Azmi. I will explain about analysis of FEMM simulation result and data observation. First one is analysis of single glass cap and pin insulator. So, based on figure 4.2, the contour profile shown the state of an insulator with pollution. From the isolation point of view, this is the worst of the two situations studied, clue to the higher isolation effect inhibition due to dielectric. The density at the iron core is higher than the other area. Figure 4.3 shown that the graph of voltage versus length on insulator. From the observation of figure 4.3, when the length of insulator is increased, the voltage is decreased. So with the pollution layer involving the entire dielectric, it is emphasized the presence of the equipotential lines inside the dielectric, which did not exist in the case of the clean insulator. This effect is due to the pollution layer electrical conductivity and permittivity. The voltage distribution along the leakage line in the cement zone has the shape of a linear function. The voltage distribution has a predominantly resistive influence considering the location of the leakage line and where the highest voltage, 11 kV, is located. However, the evolution of the tension of the total polluted insulator is inversely linear. Second one, we will continue with analysis of performance for string insulator in dry condition. We will continue with the second analysis. For a string insulator in dry condition, the difference between figure 4.6 and figure 4.7 is density of the electric field around the string insulator. Figure 4.6 shown at the bottom, the string insulator AC voltage of 275 kV. Stress is applied to the pin and the top insulator cap is grounded. The density level at the core of the string is higher than the other areas since the thermal energy is empowered by the AC voltage of 275 kV. Figure 4.8 shown the graph of voltage versus length on insulator for dry condition that is inversely linear, that shown the voltage is decreasing as length on insulator for dry condition. Pollution presence alters and exacerbates the Stokes effect in the voltage distribution profile along the glass insulator string. Next one, we will continue with analysis of performance of string insulator in wet condition. So we'll continue with the lag analysis. Figure 4.10 shows the density contour profile for 15 unit class insulator in wet condition. The density for wet condition is lower than dry condition by referring the density plot at the right side in figure 4.10. The glass suspension insulator string have the lowest electric strength. Therefore, we can suppose that the insulator string with low electric strength will have the same behavior both for tests under wet condition and under dry condition. The glass insulator strings are not the best in terms of electric strength.
Assalamualaikum. My name is Nur Zamita Arifin. For the conclusion, important conclusion about the gap and pin class insulators, reliability and effectiveness have been drawn from the FEA performed on it. According to the analysis, the insulator structural integrity is strong and can endure pollutants without losing stability. Additionally, it offers efficient electrical insulator while maintaining a stable electric field distribution and displaying little leakage current. A balanced design was guaranteed by the FEA models, uniform distribution of loads which prevented localized stress concentrations. The findings imply that there is room for additional optimization and design improvement. By examining stress concentration and strain levels, the insulator may be made lighter, stronger mechanically, and with an improved distribution of the electrical field. The insulator's behavior is thoroughly evaluated by FEA, which also helps with design optimization, boosts efficiency and reliability, and guides further research and development. Overall, the FEA study has helped the cap and pin glass insulator continue to be developed for usage in high voltage transmission line applications.